Schrodinger's brick. One particle, two states, and a mysterious brick. Can you predict where it'll end up? The time-dependent perturbation theory holds the key. So in this question, 27 out of the extras for 11, a particle of mass m is initially in the ground state of a one-dimensional infinite square well. At time t equals 0, a brick is dropped into the well. So the potential becomes V0, where the brick is. Okay, so that's on the first half. 0 for the second half, and then infinity otherwise, where V0 is much less than E1. So after a time capital T, the brick is removed and the energy of the particle is measured. Find the probability in first order perturbation theory that the result is now E2. Okay, so why do we care? Well, this problem highlights how we can have oscillating transition probabilities. Kind of weird to see, but kind of makes sense once we figure it out. Then the challenge again is interpreting these results. How do I know where the max is? Do I actually have enough probability to do so? And making sure it's not zero, things like that. And then of course, this is a relatively short problem, but the PDF is available if you want it. It's still on the Patreon page, or I can send you the link to the page. Whatever works for you, I can send it your way. Before we jump into today's topic, you should know that my goal is to break down complex physics ideas using exercises from top books. If that sounds like something you would enjoy, hit the subscribe button and join us in exploring the universe. Now, into the problem. Alright, so stop number one. Well, since the particle starts off in the ground state of an infinite square well at time t equals 0, a perturbation is introduced in the form of a quote brick potential for the duration t. Okay, and then from 11.24c, we know that if the perturbation h prime is constant, except that when it's turned on and off, then we can use equation 11.120, which is our nice dancing equation here. And what we need to note from this equation is that we have a matrix element here between the two states, as well as the energy difference. So that's what we're going to have to highlight in moving through this question. So that equation makes our lives incredibly easy so long as we can figure out what everything in it requires. Since we're dealing with the infinite square well, we know that the wave functions and energy are from chapter 2. And the two states of interest are N1 because we start in the ground state, and N2 because we were asked for what is the probability of going to E2. Both of these came from chapter 2, 2.30 and 2.31 respectively. And then we just plug in the end state and we simplify down. Nothing too crazy yet. Now we can go on to putting these into the forms that we need to calculate the quantities from 11.120. Okay, so as summarized, we are looking for a transition from m, which is the n equal 1 state, to n, the n equal 2 state, which tells us that the energy difference is just the 2 minus the 1. So now that we calculate that, common denominator, factor out pi squared h bar squared, leaving us with 4 minus 1, leaves us with an energy difference of 3 pi squared h bar squared over 2ma squared. Not too bad. Now, before we consider moving forward, let me know what you think about this theory. Drop a comment below with your thoughts. I love hearing your interpretations and questions. Now, back to finding our other quantity. Now that we have our delta E term, we can jump straight to stop number 2, which is the matrix element. And as we saw from our equation, we know that we're going to have the matrix element of the two things in between the perturbation, which is coming from 11.117. So the two states sandwiched between the perturbation, knowing that the perturbation does not affect anything in the kinetic term, only the potential term, we see that now we get a V0 0 for 0 to a over 2 in the well. Okay, so once again, in a product, this is all spatial, so we put it in the integral from 0 to a over 2, and now we just simplify. Noting that this wave function is all real, that can simplify very quickly. All right, so constants out front, no big deal. 2 over a, and then we have V0 here, because it's a constant with respect to position, but not time. And then we see that we're stuck with the product of two sine functions. So we can use the sum difference identity and turn them into cosine terms. We note that the square root and square root undo each other, so we're left with 2 over a multiplied to v0. So in the sum difference identity substitution, the 2 and 2 cancel, and now we can clean this up one at a time. So note here very quickly that this cosine is an even function. So let me write that out real quick. So cosine of x is equal to cosine of negative x. So we can drop that negative sign right here out of the whole equation. Okay, thanks to it being even, and that just cleans it up for us later. All right, so now that we have this, you could do a u sub, or you can just know that you're multiplying by this, so you need to divide by it. Whatever it is that you want to do, we need to evaluate the integral, and that's not too bad. All right, so here we have our antiderivatives, easy enough. Now we need to simplify it. We're dividing by a fraction, so multiply by the reciprocals. Now evaluate upper boundary minus lower boundary. That's what we see here. We had a lot of cancellations of the well width A, not the bore radius. And then we see here that 0, 0 on these turn the arguments to zeros. So as you see in the next step, all that whole bracket goes to 0. We like that. Now we see that we end up with sine of pi over 2, sine of 3 pi over 2, so that goes to 1 and negative 1 respectively. Fair enough. Then a negative and negative cancel. So now we're stuck in a situation where we have a over pi and a over 3 pi, so we just find a common denominator, hence the color-coded red right there, and then we can go ahead and simplify. So after we find a common denominator of 3 pi, we have 3a over here, add that with a, that's going to give you 4a. So the a from the normalization and the a from the integral evaluation cancel, and we see that our perturbation here, the matrix element of it, is equal to 4 v0 over 3 pi. So that takes care of one of our biggest pieces here, is getting rid of these two things and evaluating them. Now we're in the setup here to go straight to stop number 3 and figure out what it is that the probability shows going from 1 to 2. Okay, so as stated, now that we have all our pieces figured out, we can plug them into our famous equation, 11.120, and find out what the probability is. Matrix element here, difference of energies here, so plug it in as you see in purple, and now we just have to simplify. Okay, so squaring everything, top and bottom, we see here what happens when we do so, or at least square the bottom, square this matrix element, again, all real, so we're fine. Let's note here that we have an h bar canceling there, 2 and 2 will combine to give us 4 here. This is dividing by a fraction, so we multiply by the reciprocal, and this 4 out here is going to combine with this 4 right here to give us a 16, just to keep track of things. Again, numerically, this is all a bunch of just kind of putting things together so we can factor it out in a nice way. But definitely, once you get to this point, you're good as gold. You can stop here if you want, but cleaning it up definitely looks better. Okay, so once we do that, we see that we get a 16 here. We see m squared a to the 4th, 9 pi, so we just combine all the like terms. So we have a 9 squared, a 16 squared, v0 squared, m squared, a to the 4th, 9 squared from this and this. Pi goes to the 6th power from adding 2 and 4. And then we have h bar over 4, h bar to the 4th rather, and then sine squared of everything here. Now note that all these powers are even, so we can write them as products of 2. So as you see, every term with a red 2 in it is refactorized. So 6 goes to 3 times 2, 4 goes to 2 times 2, and so on. And what this allows us to do is take the square out of all these terms and put it on the outside of the bracket. Now, what this tells us is that the probability of measuring the energy E2 after time t is given here in our boxed area, where we have something 16 ma squared v0 over 9 pi cubed h bar squared sine of some rambunctious argument with the default time t, or the period t. Okay, and all that needs to be squared. So what makes this interesting is that the result shows that the transition probability oscillates with time. The oscillation frequency depends on the energy difference between the first and second states. And that's where all of this came from. If you remember from our formula, that came in pretty staunchly and maybe not egregiously, but it was very indicative of what's to come. So, I mean, we could say that the probability happens, it could be 0, or it could have a max of 16 ma squared v naught over 9 pi cubed h bar squared. So that's a little different than what we had seen before, where oscillating in time wasn't really a factor since we had dealt with time independent things previously. So that's pretty cool. Oh, wow. That was a quick video, but a fun one. So if this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There's so much more to uncover, and I'd love to have you along for the journey. I also want to take a moment to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful for each of you for believing in this journey. And if anyone else is interested in supporting the channel and joining our Patreon community, you can check the link in the description below. Together we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.